Alright, hello everyone. We're going to talk about 15.2. It's called Iterated Integrals, and I got a nice warm-up problem for you today. And so you can see that this integral is something that you might see in Calc 2 or maybe even in Calc 1. So I'd like you to pause the video and try to integrate this right now, and then come back and we'll start integrating it together. So here we go. We go to integrate this. We can see that we just are going to do the power rule where you add 1 to your exponent and then you multiply by 1 over the new exponent. And then plus 5, the coefficients along for the ride. X instead of 1, now it's going to be 2, divide by 2. And then we have sine here. And what's the integral of sine? And it's going to be positive cosine. Now you can see that that's true because you can take the derivative of cosine and you get that it's negative sine. So we're doing this correctly, and then the fundamental theorem of calculus says that now we can evaluate it from 1 to 3. So first we substitute in 3. And then we subtract when we substitute in 1. So that one's not so bad. Oops. To the 4th plus 5 halves, 1 squared plus cosine to the cosine of 1. Alright, so then we're going to continue on through here. You can do some simplification, add some numbers together, but you get some number. So I just wanted to quickly review what the power rule was and how you can check if you're taking the antiderivative correctly. Okay, so then in the last section we kind of alluded to the notation using two integrals. And usually that's over r. We got f of x, y, and then we had dA, where a is the area. Of the region R. So now we can say, well, perhaps we want to integrate. Let's be clear here. And let's let R be the rectangle. It's going to be all the x's and y's such that x ranges from A to B, and then the y's range from C to D. So it's just this rectangle going from A to B and from C to D, and it's this rectangle right here. And then remember, our f of x, y is going to be up some distance. Alright, so then we have some more notation. So we have our integral that we started out with. And we could really break this down now that we know what r is. And we can go from A to B, and then from C to D of our function. And this would be dy and dx. And notice that the inside integral is dy, and the smallest y value is c, and the biggest y value is d. Now, we can switch the order of integration also, but let's talk about that in a second. So first of all, what you would do is you want to work from the inside out. So we want to focus in on this integral and integrate it like normal. And since y is the variable here, let's write that y is the variable. So just like with the differential or the derivative, we get that x is a constant. So we want to pretend that x is a constant for this integral, and then we're going to integrate. And what happens is once you integrate, you're going to get a bunch of x's in your integral because they're constants. So basically, once you integrate it, you're going to get that it is some other function, but now the variable is x. So then we have our integral up here is the integral from a to b. We just said that that yellow portion is going to be some function with respect to x, and then we have dx on the end there. And then now this is just Calc 1, or depending on the integral it might be Calc 2, and then we can actually figure out what the volume is here. Okay, so let's actually do an example so we can get used to what's happening. And just remember, we're going to work on the inside and go out. So our example is going to be from 0 to 3, and then from 1 to 2 of xy squared dy dx. Now remember, we're working on the inside out, so the inside integral is going to refer to the y variable, and the outside is going to be referring to the x variable. Alright, so then we're going to here, this integral, we have x is our constant. Since there's only one term, we can take it out of the integral. We're left with y squared dy on the inside, and then we have dx on the outside. And we can integrate that right away. So this is along for the ride. We're going to focus in on that inside integral. We take the integral of that, we get 1/3 y cubed, but then we evaluate it from 1 to 2. And we still have dx on the end. Alright, so everything else is along for the ride. Let's substitute in using the fundamental theorem of calculus. It's looking good. Let's continue to simplify. So, oh, I found an error. So I already cubed it. So when you substitute in, we get 2 cubed. Alright, so we have 8/3 minus 1/3 dx. And so that's 7/3. That's a coefficient. I'm going to take it out of the integral. And now we can integrate this. So we get 7/3, 1/2 x squared, and then from the fundamental theorem of calculus, we got to evaluate it from 0 to 3. So 7/3 is along for the ride. I'm going to move this up, I guess. We got 1/2 3 squared minus 1/2 0 squared. All together, 7/3. We get 9/2 minus 0. And we can have these 3 cancels like so, and we have 21/2. There we go. So we got some experience finding the antiderivative. Now, what if we change the limits of integration? Will we get the same thing? Let's see. So I'm going to consider changing, and we're going to evaluate it and see what we get. Oops, instead of dx, dy, it's dx, dy. And so now we're going to integrate with respect to x first. So here we have y is constant. Since there's only one term, we can take the y squared out. Then we're left with 0 to 3 of just x dx, and then we have a dy at the end. We can integrate that. We have it's 1/2 x squared. We evaluate it from 0 to 3. We substitute in where we can. Don't forget that dy on the end. 1 to 2 y squared. We get 9/2, which should look familiar. We'll take the 9/2 out. We can integrate that. It's 1/3 y cubed. We evaluate it from 0 to 3. Let's substitute in now. Oh, what am I doing? Sorry. We need to evaluate it not from 0 to 3. We need to evaluate it from 1 to 2. There we go. I knew something was fishy. I didn't remember these numbers from when we did it before. There's going to be some repeats, just the way that things are. So we got 2 cubed, and then we subtract when you substitute in 1. Okay, so finishing it up here, we get 9 halves. 2 squared is 2 cubed is 8, and we have over 3, and then we have 1/3. Simplify to 7/3. This simplifies, and then we have 21 over 2. And look, we get the same exact thing. And that's where we're going to start in the next video.